All right, it's 1:50. Why don't we go ahead and begin? So next week is our first test. Tests are 60 minutes in comparison to quizzes being 30 minutes. So roughly, you should expect about twice as many problems on the tests than over the quiz. So I think the quizzes have had 5 and 6 problems. So you should expect somewhere between 10 and 12 problems for the test. It does cover basically everything in the course up until Monday's class. So the content today is fair game, then also the content in Monday's class. Basically, that ends us right at the end of chapter 13. So that's kind of a good place to stop anyway. Otherwise, it's going to be quite similar in style and whatnot to the quizzes. There's going to be some standard response style questions. There's going to be some multiple choice. There's going to be some true false, that sort of stuff. So it should be quite similar to the style and everything for the quizzes. To study, I recommend that if you haven't taken a look at these quiz and exam revision assignments, that this is a good way to study. We have a practice test, and then I've also written some stuff, just some kind of general tips for studying, I think are a good idea for the test. As well, I mentioned last time, but I didn't show you, so let me kind of go here as well. So in my folder for the test 1 stuff, like I mentioned, I also have posted a review document. So this is what I would like to go over in Wednesday's class next week, right? So we have a review day in class. So I plan on going over this. And then also there's this knowledge checklist that I made up that kind of goes through each section and talks about what are the main things that you should be able to do from these sections. So for instance, at 12.1, there's a distance between 2 points equation, right? You should kind of have an idea of how to find the distance between 2 points. You should also know, given an equation of a sphere, to find its center and radius. So we've seen that a little bit on the first quiz even. 12.2, what are the main things? 12.3, what are the main things, right? So you can kind of go down this list and hopefully identify what are the things that you still need to spend a little bit more time on to kind of shore up your skills before the test versus what are those things you say, yeah, I'm pretty good at that. I remember how to do it. I don't need to spend a lot of time on that. So I've tried to go through and do my best to collect everything. And again, this goes up through the Monday's class stuff. All right. I think that's all of my administrative stuff. Any questions about really anything before we jump into our math for today? All right, math it is then. So, switching gears here. It's 12. There we are, I made it. So today we're going to be talking about how to parameterize curves and also a little bit about arc length. So there are a couple videos to watch beforehand that shore up a few topics that maybe we won't spend so much time in today's class on. So one of them is tangent lines of vector functions. So that was in the first video. And we already talked about how you can get the tangent vector by taking the derivative of a vector function. So right, you just plug in whatever time you're interested in this case, maybe t equals a. And then with that, you can build now a tangent line, just like you used to do in our Calculus 1 days. You can also ask all sorts of interesting intersection questions, right? So for instance, if you now have, and these are the same sorts of games that we played back when we only had planes and lines, but now you can do them with any old vector function, right? So in this case, it asked, where does this curve here intersect the surface? And the technique for solving this is the exact same, right? You take the x, the y, and the z components, and you plug those things in. We can also ask questions about like find the angle of intersection, in which case, as we learned, you just need to find those tangent vectors and find the angle between those vectors. So that was the first video. The second video covered the arc length stuff. So arc length is pretty much the exact same as you did in Calculus 2. So in Calculus 2, you had arc length for just 2D functions, right? You had parametric curves and all that sort of stuff. They had X's and Y's in them. Now we're just going to sprinkle in some Z's. And so really it's not so much worse. There's just going to be this extra term with the Z's, right? And again, so this arc length formula here, you need to take the derivatives of your components. You need to square those, add them together, throw inside of a square root. That's the magnitude bit, right? Then you integrate that, and that's going to give you the length of the curve. So this is one of the applications that we can do now that we know how to integrate vector functions. All right, and so we'll get more practice on all of this sort of stuff in our problems for today. But that's the pre-class videos in a nutshell. Any questions about anything in the pre-class videos that you'd like me to spend another 30 or 60 seconds on? All right. Well then, we can go ahead and start talking about a new topic. And so far, basically, every single time we have been given a vector function, right? Someone has come up with a parameterization for us. In this section here, we're going to learn how to parameterize our own curves. And these quite often come from intersections between two surfaces. So, and again, when you have two surfaces intersecting, you quite often get some interesting curve. We played this game a little bit in 12.5. Right? We found that when two planes intersect, we found a line, right? And we tried to parameterize that line of intersection between the two planes. So we're basically upgrading that from 12.5 to talk about, okay, well, what happens if you have kind of more arbitrary surfaces? How do you find a parameterization? So starting off with, I'm going to again kind of give us the parameterization here. And I want you to think about what it means to be this curve of intersection, right? So this means that it must satisfy both of the surface equations. It's got to be on the first surface, and it must be on the second surface. So that's really what it takes in order to be not just, a point of intersection, but a full curve of intersection. So I'd like to verify that this thing that I've handed to us, right, actually is the curve of intersection. It actually satisfies both of these things. And so in order to do that, right, whenever we have a parameterization, we have an X component, we have a Y component, and we have a Z component. And so a good way to verify that this is actually a part of the surface is, right, you take those components and you plug them in exactly where you see the X's, the Y's, and the Z's. So let's go ahead and start off by doing that for this first surface. So this first surface is a cylinder. It's a circular cylinder. It's even like our favorite type of cylinder, but it's missing a variable, right? There's no Z's. So it's going to kind of go freely in this Z direction. And in fact, this one has the picture over here, so we can really even see it. But again, I'm going to plug in my X, which is 2 cosine t. Everywhere I see an X. I'm going to plug in my Y stuff, 2 sine of t. Everywhere I see a Y. And supposedly, if it's a part of this surface, when I square these things and add them together, I ought to get 4. Otherwise, it's not a part of this surface. It's not on the surface. So luckily, you can kind of see that we're going to have this good old cosine squared plus sine squared sort of deal. I can factor out the 4 from both of those terms. And cosine squared plus sine squared is always equal to 1, no matter what the t is. So that's quite nice. And so yes, this is equivalent to 4. So this parameterization seems to work for the first surface. I'm happy with that. Let's look at the second surface. The second surface is a plane, right? And we could find the normal vector and all that sort of stuff, but I see everything's nice and linear. And in fact, in the picture over here, we can see it. It's at some slant. And I'd like to verify that, again, that this curve that I'm going to plug into the surface, satisfies my equation. So let's go ahead and do that. I see I have a Z on the left-hand side. So on the left-hand side, I'm going to write 2 cosine t plus 2 sine t minus 1. And then on the right-hand side, I have x plus y minus 1. So I have x plus y minus 1. Okay, well, yeah, it looks like this exactly, the left side is exactly equivalent to the right side. So yes, this is also satisfies that second surface equation. So it satisfies both surfaces, and so therefore it is this curve of intersection. So if I was to maybe imagine what this shape is, now we're going to get some sort of circle at a bit of a slant here, because it's both on my cylinder and it's on my plane. All right. Now I have a hypothetical for you before I open the floor to any questions. Suppose, some other students said that they found the curve of intersection and it was 2, 0, 1. Right? So just some numbers here. So 2, 0, 1. And my question is this correct? Why or why not? So 2, 0, 1, again, is going to be maybe like right here or so. Going to be some point on this. So what do you think? Are you happy with that for the curve of intersection? Probably not, right? I mean, it's a point of intersection. It's one possible answer. It's like if I asked you to find when x squared is equal to 4 and you said 2. You have an answer, right? But it's not all of the answers. You haven't solved the entire problem. So although this is on the curve of intersection, sadly, it's not the full curve of intersection. So no, not the full curve of intersection. This comes up quite a bit, and we'll see an example of it later. That basically, if you ever have to induce a square root, in order to get the full curve, you have to have the plus square root and the minus square root, right? And so you can't really do that in just one nice equation here. And so there are very clever ways of getting around this. However, right, my thing, the easy storyline that I want to give you is that if you see a square root, if you have to take a square root when trying to find a curve of intersection, I'd be a little bit wary, just because you may only be getting half the curve, right? If you choose the positive square root, you get 1/2. If you choose the negative square root, you get the negative half, right? Again, but it's just half. So you won't get the full curve of intersection. So if you end up needing to take a square root, I'd be a little bit worried. So again, we'll see an example of that coming up. All right, so ultimately, the question is, how did I come up with this thing here, right? This 2 cosine t, 2 sine t, and then the 2 cosine plus sine minus 1, right? How do you come up with this? And you played this game a little bit in calculus 2, right? Of course, it's harder now because we have the 3 variables. But ultimately, if you believe that the curve of intersection is going to be a closed curve, that means it doesn't go on forever. It's going to start and end at the same spot eventually, right? Like a circle or an ellipse, that sort of thing. Then it turns out cosines and sines, using those in your parameterization, are a good idea. And as you saw in this last one here, we do have, first of all, it is closed. It doesn't go on forever. It's a circle. Well, it's at a slant, so it's an ellipse. And notice that we have the cosines and sines here. But they're not just cosine and sine, right? There's a 2 in front of them. So we have to talk about, like, how do we know that there should be a 2 there? But let me finish what goes in this box here. Otherwise, if it seems like the curve is going to go on forever, I would try either x equals t, y equals t, or z equals t. And as you do more of these problems, you'll get some intuition maybe for which of these might work out and which of them might not. But the big thing is, if you kind of run into a dead end, the big thing is to just start over, right? Maybe try, instead of x equals t, try y equals t. So I'll also demonstrate what it looks like to kind of dead end, to start off maybe down some wrong path and realize, okay, this isn't going to work out. I need to try something else. All right, so let's try a few of these. I have a few interesting surfaces here, and I'd like to find the vector function that represents the curve of intersection. So my 2 interesting surfaces are right here. And again, when I'm looking at this, kind of similar to this first problem, I notice that I have basically a circle, right? It's a circle in the xz plane. Usually circles, we like them with x squared plus y squared equals r squared, right? But this is in the xz plane here. And then if there's some other interesting surface, right? And so I'm thinking that maybe this curve doesn't go on forever. Maybe it's a closed curve. And again, kind of seeing that these two numbers here have to sum up to give 9 once squared, right? That gives me an idea that maybe this doesn't go on forever. And so in order to satisfy this, I'm going to be thinking about, again, the Pythagorean theorem, essentially is what this is, for trig functions. And I think about, okay, well, what if I let x be cosine and z, I guess there's a z here instead of a y, fine, z can be sine. And you'll see that this doesn't quite work out, right? When I plug this in and I square these and I sum them together, right, I get 1. I don't get 9. It is constant, that's nice and everything, but it's just not equal to 9, it's equal to 1. So anyone have an idea, how can I adjust these in order to get 9 instead? Yeah, in the back? Exactly right, yes. And you should remember this a little bit, I hope, from Calculus 2 days, right? Because you did some polar stuff. And so you remember from polar, there was something about r cosine theta and r sine theta. So that's essentially what we're stealing from here. And the r is 3 in this case, right? The radius of this circle is going to be 3. And so that's why we're using that. So now you can double check. If you square these and sum them together, yes, this works out. It gives you 9. So I'm happy with these as my parameterization. So I have x in terms of t, and I have z in terms of t, but I don't have y yet in terms of t, right? I need these 3 equations in order to get a good parameterization. It needs to have an x, a y, and a z component. So luckily, though, I have y equals in terms of x's and z's. And I know what x and z are, right? So I can go ahead and plug those in. And everywhere I see an x, I'm going to put 3 cosine of t. So that needs to be squared. And then z is supposed to be 3 sine of t. So what's 27 cosine squared sine to the first? So now I have my set of parametric equations. I have x in terms of t, y in terms of t, and z in terms of t. If I want to make this as a vector function, right, it asks for a vector function, then I'll go ahead and put them, maybe r of t equals, and I can do my x stuff. I can do my y stuff. And I can do my z stuff. Similar to lines and lines of intersection back from 12.5, if you don't put any restrictions on t, the assumption is that t goes on forever. T would go from negative infinity to positive infinity, which is okay, right? Because that means you are going to hit all of the points. You do get the full curve of intersection in this case. However, you do hit all of the points infinitely many times because, again, this is a circle. We're going around on this x squared plus z squared equals 9. So really, in order to get the full curve of intersection, I only need to go from 0 to 2 pi. That's going to guarantee that I get the full curve, but I'm not double counting any of my points or triple counting or anything like this. So again, technically without this, it is correct right now. I'm just thinking ahead, right? Eventually we may get an arc length question, right? That say, find the length of this curve, right? In which case you want to make sure all the points are counted, but you don't want to double or triple count them. You don't want to keep on going around this circle. Otherwise, right, it's just going to keep on adding up, right? You're going to have too much length, and it's not really the true arc length. Or likewise, in chapter 16, we're going to be doing other things. And so it's good to hit every point once, but ideally not more than that. So this is just a good habit to get into. All right. Any questions on this one here? All right. Well, let's try a harder one here. And as I promised, I wanted to kind of showcase what it looks like to do it wrong a few times, to kind of hit a few dead ends. So that way we can realize that and kind of back up and try something else. So maybe looking at this, I could convince myself, maybe, that I see another x squared plus y squared in here. This one isn't equal to a constant on the other side. So it's not the exact same setup, but still, maybe because of the x squared plus y squared, I could think about maybe this is a closed curve, right? Maybe sines and cosines would work out very nice here, right? And so maybe one of my things that I want to try out is if x is equal to 1 cosine t and y is equal to 1 sine t, and just see kind of what happens if I take that as my starting assumption, again, because I see the x squared plus y squared. And so that's what we did last time, and it worked out for us. So if I go ahead and plug these things in, notice that in my first equation, I get that z is equal to the square root of, and I'd have cosine squared plus sine squared. So that's going to be the square root of 1. Again, cosine squared plus sine squared is equal to 1, no matter what the t is. So this tells me that z is exclusively equal to 1. No matter what the time is, z is always at a height of 1. Now compare this if I look at my second equation, right? Because I also have a second equation that has z's as well. And in there, it says that z is equal to 1 plus y. And now we can see that actually both of these things can't be true. Z can't be exclusively equal to 1, and it also wiggles back and forth, right? With the sign, it's going to be wiggling a bunch, right? And so we can see that, okay, something bad has happened. We have some conflicting information. And so it turns out that this curve here is not going to be a closed curve. So that was the issue that I ran into, and that's kind of why we get this conflicting information. So let's try something else. Since it's not a closed curve, since the sines and cosines didn't work out, the next step is, well, maybe starting off with letting either x be equal to t or y be equal to t or z be equal to t. And I can see here, if I guess y was equal to t, I could solve for z very fast, right? So y equaling t means now that in my second surface, that z is just going to be equal to 1 plus t. So I have 2/3 already, right? Again, I need an x, a y, and a z. And if I'm saying y is equal to t, I get the z very fast. So now all I need is x, right? And so, okay, my other equation has an x in it. Hopefully I can solve for x with this. So let's go ahead and plug these things in. So for instance, z is supposed to be 1 plus t, 1 plus t. And then on the right-hand side, we have x squared. And again, ultimately, we're trying to solve for x. And then y is supposed to be t. So this is going to be plus t squared, since it's a y squared there. All right, now, trying to solve for x, I can square both sides. I can rearrange. So let's see, 1 plus t quantity squared minus t squared. And then I would need to take a square root. And this is what I was getting at earlier on the first page. In order to solve for x here, I had to induce a square root, which means that really there's a plus and a minus. If I want to get the full curve, I need to include both of these things. And yet a vector function means that, well, there's this whole stuff about vertical line tests and whatnot, right? This plus and minus isn't going to be a function. And so that's my issue here, is that because I've had to take a square root, and in order to get the full curve of intersection, I need both the plus and the minus. I can't just choose one of them, right? And so again, this is kind of me showcasing a bit of a roadblock here. So a very reasonable thing to start with, y equals t, but we just have to realize that sometimes it's not going to work out, and we have to pause and try something else. So finally, the right answer. Looking at this, I mean, I really liked trying y equals t. I thought that was working out well. So I'm going to try here x equals t. So x equals t as our starting point, and try to see if we can solve for these other things here. So if x is equal to t, we have what? Z is equal to the square root of t squared plus y squared. That one I can't solve, right? I have both z's and y's in it, right? So I'm going to need to use my other equation. Maybe I'm going to substitute it in everywhere I see a z, a 1 plus y. Okay? 1 plus y. Okay, so now hopefully I can solve for y by itself. So again, let's square both sides. I'm going to expand this out this time. So when I expand out the left-hand side, again, I had to square all of it. So it's 1 plus y times itself. So I have to FOIL that, and this is what I get. And on the right-hand side, when I square that, this just cancels with the square root. And now I was worried because I thought I was going to have to take another square root, right? In order to solve for y equals, I was worried I was going to have to take a square root. But luckily, I don't. The y squareds both cancel. And so now, in order to solve for y, let's see, I'm going to have 2y is equal to t squared minus 1. So y is going to be equal to 1/2 t squared minus 1/2. So just dividing by 2 across the board. So now I have my x and I have my y, but I still need my z. Well, luckily, and again, you should be able to plug this into either one at this point, but the second one here is looking way simpler. So I'm going to go ahead and plug it into there. Z is equal to 1 plus y. Notice at no point did I need to induce a square root. So I never had to do this stuff with the pluses and the minuses. And so this is going to be my correct answer. So t 1/2 t squared minus 1/2 and 1/2 plus 1/2 t squared. This is going to be a sort of a parabola shape. It does go on forever. So leaving your answer just like this is fine. Or if you did want to specify, you're going to want t to go from negative infinity to positive infinity. Okay, so the main thing that I want to try to get across is that these things are difficult. You're going to mess some up here and there. And the big thing is that don't just let it waste a bunch of time. I'm thinking especially for like quizzes and exams and stuff like this, is that I've seen students who they don't know what to do. They don't know the right path. And so they don't do anything, right? They kind of freeze a little bit, right? And my claim is that you should choose some path. Hopefully, as you do more and more of these problems, you're going to get it right more and more often. But when you encounter something like this, that it doesn't work out, okay, well, I know something else to try, right? Instead of y equals t, let's try x equals t. And just kind of back up and keep going. All right. Any questions on these here? So we'll go here and then there. Okay. They're a bit of trial and error, but again, you get better at them the more you do, right? So unless if you can visualize and like 100% guarantee that you have a closed curve, right? How do you know that it's truly closed? Because closed is kind of, when you look at it, it doesn't go on forever. So you're going to have to try. Maybe if you think it's going to be closed, you can try the sines and cosines, but if it doesn't work, you have to back up and try something else. Yeah. So yeah, it's really hard to find a technique that works for every single problem out there 100% of the time.
So for the problem we just did, it wasn't a closed curve.
Nope.
Z ended up equaling like 1 and then 1 plus sine t, and that's why it's not a closed curve.
Yeah, so in fact, we can sketch this one pretty fast. If you remember from 12.6, I'll go a little bit fast here. This would be the equation of a cone, right? So once I've taken the square root and I've solved z equals, and I've chosen here, it's given to us as the positive square root, right? It could have also given us the negative square root. It's just the problem didn't happen to choose that one. So it turns out that this is the top half of the cone where the z's are positive. So that the positive square root of x squared plus y squared equaling z is the top half of a cone. The other surface here is a plane at a slant, right? So it's happening to miss x variable, but still everything's linear here. So this is going to look a bit like this at a slant. And the curve of intersection that lies on both of these, it turns out to be this parabola. And again, it's going to go on forever, right? Because the cone's going to keep on getting bigger and bigger. The plane's going to keep on going, but it's going to end up being this parabola. And so that's why you can see a couple of these things here. They're very parabolic, right? There's the good old quadratics in them. So yeah, in this case, it's not a closed curve. It goes on forever. And that's why the x equals t or y equals t or z equals t is going to work for this. Good. Any other questions? Yes, here. If you use the sine and the cosine, this works well when you have a closed curve. If you don't have a closed curve, you end up getting some nonsense like this, where z can be parameterized in two different ways depending on what surface you're looking at, and they're in conflict with one another. So that's not actually on both surfaces. So that's what happens when you try to apply this technique when you don't have a closed curve. You end up with a little bit of conflicting information. All right, so I think this is, again, like I mentioned, these are kind of tougher style problems, and that's kind of why I wanted to make sure to spend time in class on these rather than making a video out of it. But we also owe it to ourselves to talk a little bit more about arc length. We haven't seen many of the full strength problems in the pre-class videos. And so it'd be good to see a few more and kind of how difficult they can become. So this is a common prompt here. Find the length of this curve, this vector function, and it has to give you a range. It has to give you a starting and an ending point. So anytime it says, right, finding a length of a curve, this means, according to our formula, that we are calculating out this integral. This is the integral that gives arc length. So we just need to kind of carefully build up this inside function here, this integrand, and then that's the thing that we're going to integrate. So maybe as a first step, I need to take the derivative. And then as the second step, right, we're going to take the magnitude of that derivative. And then that's the thing that we're going to plug in and integrate. So, okay, working kind of inside out. First, we take the derivative. So 2t and, t squared. So again, this is me working across my function that was given and taking the derivative of each component. Now we need to find the magnitude of this. So the magnitude, this is the exact same as it was back in 12.2, right? We're going to take all of our pieces, we're going to square them, we're going to add those together, and we're going to throw them inside of a square root. Well, we take one line to simplify at least. 4 plus 4t squared plus t to the fourth. And so in order to find the length of this curve, we are going to be integrating. Now this curve, it's specified, we're only interested in the length between t equals 0 and t equals 1. So our bounds here are from 0 to 1. And then our function here, this magnitude of our derivative, is this 4 plus 4t squared plus t to the fourth. That's what we'd like to integrate. So here, now officially, really all of the new Calc 3 stuff is done. Now we've set this up, and the question is, how do we integrate this using our Calc 1 and our Calc 2 skills? Right? And so looking at this in general, I get nervous anytime there's a square root around. Remember, when there were square roots around, in the general case, this is really the impetus for trigonometric substitution. This is where you really need to use trigonometric substitution quite a lot if you just choose a random problem with the square root in it. So that means that these have to be carefully constructed unless we want to make it a trigonometric substitution style problem, right? So luckily, though, there are ways that you can sometimes get rid of the square roots or deal with these using like U substitution or perfect squares or things like this, where you don't need trigonometric substitution. So those ones you see a lot more in our class, just because, again, we're not trying to test you on this Calc 2 thing so much. So looking at this problem here, anyone have a clever algebra thing that we could try to maybe make some progress, maybe help us get rid of the square root? Oh, yeah, we'll go here. Yes. So this thing in here, turns out you can factor it, right? It's kind of quadratic-esque, right? If you let u be t squared or something like this would be like 4 plus 4u plus u squared, right? So it's quadratic-esque. And if you factor it, you get 2 plus t squared times 2 plus t squared. AKA, right, it is a perfect square. It's just something multiplied by itself. So it turns out, let me go ahead and just write it as, again, a perfect square. This is one of the ways that, again, we don't want to kill you with trigonometric substitution and take a very long time. So this is one of the ways that sometimes you can nicely cancel out that square root and actually make the integral reasonable. So we have the square root of something squared. Those nicely cancel and give 2 plus t squared dt. Now I can integrate that. So when I integrate this, I get 2t plus 1/3 t cubed. Evaluate that from 0 to 1. I'm going to get 2 plus 1/3. I lied to you only once during this. And that is when you have the square root of something squared, those don't exactly just cancel. Technically here, this is the absolute value, right? So one way to create the absolute value, a very reasonable definition for it, is that you take something, you square it, and then you square root it. And again, this is with the positive square root, and that's what guarantees it to be positive. So notice, right, if I took like a number like -4 and I squared it, I would get 16. If I then plug that into a positive square root, I don't get -4, I get +4. So I don't get what I started. It's actually positive now. So technically we need some absolute value signs here. Now the next step is for me to say that we really don't need those absolute value signs there, right? So the thing is that t ranges from 0 to 1. My lower bounds are 0, and my upper bounds is 1. So the things that I'm plugging in for t, worst case 0, best case 1, right? And we're taking that and we're adding it to 2. So that means that the things inside of this absolute value range from 2 to 3. They're already positive. And so if you have something that's already positive, the absolute value doesn't do anything. And so that's why it was kind of forgivable for me to not include the absolute values there. But you do have to be careful with your bounds and kind of your function and all that sort of stuff. So if you incur one of these, do think about and make sure that the absolute value truly doesn't matter. All right. Any questions on this problem here? Yes. Yeah, so back in Calculus 1, you did, at least here at MSU, incur these sorts of problems, and you need to break it up. So you need to break it up, when is it positive versus when is it negative? So if I wanted to, let me kind of make my life a little bit easier. I'm gonna, should make this probably green or something like that. So here's an alternate problem. If you needed to evaluate this here, notice if I plug in t's ranging from 0 to 1, what's inside of the absolute value stays positive. When I plug in t equals 0, I get 1. That's perfectly positive. And as I get closer and closer to 1, then I'm going to be subtracting away 1 squared, and that's going to give me 0, right? So I'm still technically in the positives, right? Or at least non-negatives. So I would say from 0 to 1, the absolute value doesn't matter. Then from 1 to 2, the absolute value matters, right? From 1 to 2 here, now when I plug in things that are bigger than 1 and approaching 2, I have 1 minus, and I have enough stuff in the negatives there that it's going to certainly be negative overall, right? So for instance, when I try to plug in 1.5 or 2, we just do 2, right? So 1 minus 4, that's negative 3, right? But the thing is that I've broken it up to when it's positive and now when it's negative. So when it's negative, we know the absolute value is just going to take this and apply a second negative to it to force it to be positive. That's the way the absolute value works. So if this thing is negative, which it is from 1 to 2, the absolute value acts on it by applying a second negative, because the negative of a negative is positive. And so that forces that second part to be positive as well, right? And now we can integrate each one of these individually. So that's how we can deal with if the absolute values did matter. But again, you can see this is taking time, right? This is a bit of a nuisance, right? And so again, we really have to weigh when we're making, especially quiz and exam problems, right? How much do we really want to get into the weeds for this? I haven't seen a problem where the absolute values mattered in a while on a quiz or an exam. Not to say it can't happen, right? But I just haven't seen it in a while. Yeah.
You didn't really have a negative ever if you did like a magnitude because you're squaring each term. So each term is going to be positive, right? So you would never really have to say that. I mean, that's
Yeah. Yeah. So this is a bit of a fictional situation here. So because we are squaring all these things and adding them together, it's very hard to come up with this. That's absolutely true. We'll see another situation here for this next problem that, again, you do need to think about if the absolute value matters or not. But again, the answer is going to be no. Good. All right. So I'd like to give you, let's see, maybe 60 seconds or so head start. Same sort of prompt here. The words that essentially mean, hey, find the arc length. You're going to run into a slightly different hiccup with this one. And hopefully you can overcome it. If not, we'll go over the results together. Bless you, bless you. Another 30 seconds or so. Again, get as far as you can. All right. So I would say first off, as you're doing more and more of these problems, this is probably a good minimum amount of work to show, like for quizzes and exams and whatnot. I wouldn't skip any more steps than this, right? But you can take the derivative of each piece and then throw that into the magnitude, maybe all in one line. I think that's good, kind of a good maximum here for the amount of stuff you can do in one step. Simplified down to my second step, working with all those squares. And now again, we get to a situation where I'm back in my calculus 1 and 2 days, essentially. I've done the setup for arc length, but now I need to evaluate this integral. Last one turned out to be a perfect square, which helped us cancel out the square root very nicely. Sadly, try as I might, this one's not a perfect square. So does anyone have a way forward? Maybe something else? Yeah.
Do you think technically you can factor out t squared from both elements and then take that outside of the square root as just
Good, I like it. So the claim was that last time we factored and that helped us, right? And although this isn't a perfect square, it doesn't factor out very nicely. We can take the GCF, the greatest common factor, out, in which case is a t squared. So we have something that looks like t squared, then 4 plus 9t squared, something like that. And square roots, they behave very nicely over multiplication. So it is a true theorem that if you have the square root of a times b, that this is equal to the square root of a times the square root of b. Again, so long as these things are all positive. What's not true, what sometimes I understand the desire for it to be true, but sadly it doesn't work out, that if you tried this with addition, something like that, this is not equal. So you can play this game with multiplication, but you can't do this with addition, right? A simple example of this is if you just do ones. So the question is this equal? So if ever you're on a quiz or an exam and you think, I want to do this, but I don't remember if it's right, just try plugging in specific things, right? So now on the left-hand side, this is square root of 2. Your calculator will tell you that that's around 1.41 change, right? And then on the right-hand side, you have, well, 1 plus 1, you have 2, right? So this is not the same thing. So, okay, that one doesn't work out, but with multiplication, it does. And so then the last bit is that you were claiming that you can then simplify. And again, this is where technically this is an absolute value here, right? Because you have the square root of something squared. But again, luckily our t's range from 0 to 2. So these are all positive things. If this had gone from -1 to 2, that would be an issue, right? But luckily the t's are all positive. Okay, so this is a way that we can rewrite it. And the question is this a good path to head down? Is there a way that now with this, that we can make progress and that we can actually solve the problem? My claim is that yes, we are headed in the right direction. Do you see what to do next?
Set 4 plus 9t squared equal to u.
There you go. Yeah. So a u substitution. So u substitution, certainly fair game in this class. If u is equal to this inside function here, inside of the square root, then when I calculate out du, I get 18t dt. And this gives me a lot of hope, right? Because I have this t dt, right, to kind of trade in here. So then if I go ahead and, well, let's see, I'm going to write this, as du divided by 18 is what I'm going to be trading for t dt. And now start substituting some of this stuff in. So this is going to be square root of u, and then I'm going to have my du divided by 18. So that's all looking good. Now I can integrate, right? The square root is the same thing as being raised to the 1/2 power. So when I integrate this, I just have to use the power rule here. So I'm going to raise my power up by 1, and then I'm going to multiply by the reciprocal of that new power. And I guess I have this 1/18 that's along for the ride there. Now that I've integrated, I can go ahead and plug back in my t's instead of u's. So let's see, this is 2 and the 18 will cancel a little bit. So I guess I have 1/27th, 4 plus 9t squared, raised now to the 3/2 power. And I need to evaluate that from 0 to 2. So now we have successfully integrated thanks to u substitution. So let's go ahead and plug in and find our final answer. We have this 1/27th again along for the ride here. When I plug in 2, it looks like, let's see, 2 squared is going to be 4 times the 9 is 36, plus another 4 is going to be 40, raised to the 3/2. And then when I plug in 0, I get, well, 0 plus 4. So I get 4 raised to the 3/2. And this right here would be a perfectly reasonable thing to type into WebWork or plug into your calculator and get a decimal answer to 3 decimal places for a quiz or for an exam. If it did happen to show up as a multiple choice problem, it's possible that this right here, if you just plug that into your calculator, you'll see that this actually simplifies down very nicely. The 41 doesn't, but the 4 does. So 4 raised to the 3/2 power is just equivalent to 8. So if it does show up as a multiple choice, it's possible that instead of 4 to the 3/2 there, they could put 8, and that would be a correct answer as well. So, all right, well, again, one page you didn't quite get to. I will post the solutions to this by 4 o'clock today on D2L. So please consider this, and then when you're ready to take a look and see what the answers are, you can check on D2L. So I'll stick around if there are any one-on-one questions. Otherwise, have a great weekend, and I will see you guys come Monday.